Electromagnetic waves always involve both electric and magnetic fields, although sometimes we may ignore the magnetic field and look only at the electric field, or we may ignore the electric field and look just at the magnetic field, but they are always propagating together. The propagation direction of the wave, which direction the wave is traveling, the electric field and the magnetic field form a right-handed triple vector that are all perpendicular to each other. So, for example, if I have a wave that is traveling in the x direction, so if my direction of travel is in the x direction, my electric field might travel in the y direction, and then going, say, in or out of my page in the z direction is going to be my magnetic field. Or we could represent that kind of in three-dimensional space as x, y, and z, and then our travel direction would be in the x, our electric field might be in the y, and our magnetic field might be in the z. The values of the electric field and the magnetic field are going to depend on two variables. X, which is going to be the position, and time. So at any one instant in time, say my electric field here might change and move in space, but while it's moving in space, it might change in time. So this ends up with highly complicated equations to describe what's going on. What this ends up looking like is our sources of these waves are going to be sinusoidal. That's why we call them waves, because they will oscillate like waves. So if we have our x direction to the right, that might be our direction of propagation. Our electric field is going to increase and decrease sinusoidally, but it's going to oscillate in the y direction. So going up the page, positive y direction, or going down the page, negative y direction. And it's going to get larger and smaller in magnitude over time, and also in space. Our magnetic field right here, if you picture that, like when it's the positive z directions, like coming out of the page at you, the negative z direction is going into the page, so that these are 90 degrees to each other. They are also both 90 degrees to the direction of propagation because this wave is moving. So what's going to happen is this point in that electric field is actually going to propagate. And if I was to look at a different instant in time, that wave is going to have shifted over time. And then our magnetic field is also going to shift with it. So if I was to look at a different instant in time, you're going to end up with a slightly different wave. Sorry, these are harder for me to draw. So you're going to have this wave propagating in both time and space, like the doctor. So the basic structure of waves are going to be sinusoidal. So we have different things that we can define. So the first thing that we can define is the amplitude. So the amplitude is either going to be E for the electric field. E is going to have units of newtons per coulomb. Oh, I guess that should have been more like that. And then B from the magnetic field, which would have units of Tesla. So in a wave, either electric field wave, magnetic field wave, or an EM wave in general, the amplitude is the distance from the center line to the peak. So that's what our amplitude is. It's how big is it? Like, what is the maximum value that it can have? We also call the amplitude the intensity because it's constantly changing, but it changes so rapidly. We're really interested in those maximum values for like our intensity there. So our next value is the wavelength. Wavelength gets the symbol of lambda. That's the Greek lowercase lambda. The units for wavelength are generally measured in meters. And this is going to be the distance from like crest to crest or from trough to trough. So that is a spatial distance. We also have frequency. Frequency is the number of times that it repeats. So we usually use that curved lowercase f for frequency. And then the unit is the hertz. A hertz is the same thing as seconds to the -1 or a per second. So cycles per second. And a low frequency wave in a certain amount of time is not going to oscillate very much, whereas our high frequency wave is going to go through more complete cycles in the same amount of time. So this was a time span. You had low frequency versus high frequency waves. And then wave speed is the rate at which energy is transmitted. So remember that, like, when you have a wave, sometimes the wave propagates through space, sometimes it's just the energy that propagates through space. And so this is the rate at which the energy is transmitted over a distance. So it's still going to be basically distance over time for wave speed if it's constant. So that's why the units are meters per second. But we use this, it's technically nu, the Greek letter nu, but it's almost like kind of like a curvy V for wave speed. So a little more about wave speed. So it's going to be distance over time, because we're going to assume that it's constant. So if we wanted to find that distance is the wavelength for one period, capital T. So in if I go through one complete oscillation, okay, along that sinusoidal axis, the distance that wave travels will equal the wave speed, and the time would be that period. We already know that period is 1 over the frequency, so if you substitute in 1 over frequency and then do a little rearranging, we get that our wave speed is equal to wavelength times frequency. And you would have seen this like in chemistry, because you do this for the energy for that is given off like when electrons fall back down and glow and create the different colors of light, and that is the wave speed. So that is true for any wave. But in particular, our EM waves are going to travel at the speed of light, and in a vacuum. Anyways, in a vacuum. And as long as we're not too close to any sort of major gravitational fields, like near a black hole or anything like that, our EM waves are going to travel at the speed of light. So that's 3.00 times 10 to the 8th meters per second. It's also the same thing as 1 over the square root of mu naught E naught. So remember, E naught is our electric permittivity of free space. Mu naught is our electric permeability of free space. Sometimes you see this written as C squared is equal to 1 over mu naught E naught. Is another way that's written. It's just rearranging with the square root there. But that's why mu naught and E naught are fundamental constants, is because they are what constitute the speed of light. So if we were in another material that wasn't vacuum, the value for mu and the value for E actually change. So therefore you would get a slightly different value for the speed of light. Now, you would have to know partial differential equations to be able to solve those differential equations. You will never be expected to do that. But if you were to solve them, this is a pair of equations that represent the solution to those. So these describe the sinusoidal functions of those waves as they vary in space and time. So these Emax and Bmax are the amplitude of the waves, and they vary both in terms of x and t. So when we're looking at this wave, this equation, there's some very specific variables. The first one is the wave number k. The wave number k is a placeholder for the constant that is in front of x. This is not any of the other k's that we have seen. It is not kappa, which is the dielectric constant. It is not Coulomb's constant, even though it's a k. It's not also k, which is the spring constant. In this case, the wave number k is related to the wavelength. And it's really there just to simplify that equation down. So instead of having to write EY is equal to E max, sine of 2 pi over wavelength minus, times x minus omega t, they're like, we're going to call this like 2 pi over wavelength. We're just going to call this k, just so we can simplify our equation down. That's what the wave number means, okay? It's just a placeholder for the expression 2 pi over the wavelength. The wavelength relates to the space dimension that we have in our equation. So for example, I can look at this electric field equation as a function of x, or I can look at the electric field as a function of t. So if I was looking at it in terms as a function of x, my sine function would look something like this. And the wavelength, lambda, would be one full wave in space. Okay, so my wavelength would be one full wave, one full oscillation of the wave in space. Okay, that's what our wavelength is. It's related to our spatial dimension. Now, you have seen angular frequency and the frequency f before. These guys you would have seen in your oscillations, simple harmonic motion, mechanical waves, and so forth with that. So our angular frequency is 2 pi f. So when we once again look at our electric field equation, when we look at it as it varies with time, you're going to get this kind of sinusoidal function, right? Over time as well, because it's going to oscillate sinusoidally in both time and space. When we look at this, if we were to find the time for one complete oscillation, that's our period. Our period is 1 over the frequency. And now we're saying that that angular frequency is 2 pi times f. So lots of different ways that you could represent the rate at which the oscillation is oscillating in time. Okay, you could do angular frequency, regular frequency, you could talk about the period. Now notice that both of the electric field and the magnetic field are going to have the exact same values for the wave number and for the angular frequency. And that is because they are intrinsically linked together. They cannot oscillate at different rates. They cannot have different wavelengths without doing a bunch of high-level differential equations in physics that are well above the level of this course. I can't prove that these are true to you. So you just kind of have to accept, unfortunately, that this is the way that these waves behave. Now, by definition, the speed at which the wave propagates, we would use to represent with like a v in general, okay? And that would be distance over time, assuming that we're at a constant speed. Now, if you think about it, the distance that a wave travels in one period is the wavelength. So the distance would be a wavelength, and our time would be a period. So since our period is 1 over frequency, what that gives us is that our wave speed is wavelength times frequency. Now, if we are in a vacuum, I don't know if that's vacuum spelled right, that's one of my worst words, then that wave speed is the speed of light if we are in a vacuum. And air is close enough to a vacuum for our purposes 99% of the time in this class. So what we have is we have a definition of C as being 1 over the square root of mu naught E naught. And that comes from the solution to those differential equations on the previous slide. So our wavelength times frequency is also the same thing as our angular frequency over K. You could show that by substituting in these two definitions here, and you could prove that that was actually true. So that gives us kind of the parameters that we use to describe the wave. We have our maximum electric field strength, our maximum magnetic field strength, and then we have our wave number, wavelength, angular frequency, and our wave speed itself. Now that we understand a little bit about what these variables mean, I want to go back and kind of dissect some of these variables a little bit. So remember we said that our propagation direction and our electric fields and our magnetic fields all have to be 90 degrees to each other. But how do I know which is moving in which direction? It's going to depend on the subscripts that are given. So the first thing that I can notice here is that both of these are in terms of x. If the variable that is attached to k is an x, that is going to be the direction of travel. So in this case, our direction of travel is in the x direction. They are giving us subscripts here for y. That is telling me that my electric field is oscillating in the positive and negative y direction. By process of elimination, if all I had was this electric field equation and no one gave me the magnetic field, I could still know the direction of oscillation of B because it has to be perpendicular. So that means that my magnetic field would have to be in the positive and negative z direction. So with the equations on the previous slide, we can come up with several different relationships here. And that is based on the ratio of E max and B max, or E and B. So if you take those equations, that E is equal to E max sine of kx plus omega t, and you have your B is equal to B max sine of kx plus omega t, or minus, plus or minus really for those. If you were to divide those, what ends up happening is that the sine term is identical in both, and so that cancels out. So that tells us that E over B is equal to the same as E max over B max. So those ratios stay the same. We can also use some other of the relationships and definitions to show that this is also equal to omega, which is our angular frequency, over k. But proving that requires calculus, which we don't have, so we just kind of have to take that on faith that that ratio is also going to equal the omega over k. But we can also show that that does equal c, which is our speed of light, by using our definitions for omega and k. Because we know that our omega is 2 pi f and k is 2 pi over lambda. So if we were to simplify this, the 2 pi's cancel, leaving us with a 1. And then what we can do is we can then flip and multiply. So that actually equals wavelength times frequency, which we know is wave speed. But for light, our wave speed is equal to c times speed of light, which, when we mentioned earlier, is the same thing as 1 over the square root of mu naught E naught. So we can see that all of these things are equal to each other. So this is kind of cool. You don't have to have it memorized. It's on your formula sheet. But given any pair of information, there's so much that we could find. So if we know E and B, we can find anything else that we have. Or we've got our speed of light c, so like E over B is equal to c. So since we know our speed of light, if I know my electric field, I can calculate my magnetic field with that. Or if I look at this section here, I need any two pieces of information, I can find the third. Or given that information, I could find omega, or I could find k. So you can find all of these different things out about your waves with just a small amount of information. I think I've got another video that gives an example of that. So with this first simulation, we are going to look at just an electric field. There is a magnetic field that is going to be oscillating, but we aren't going to be able to see it in the simulation because it's too complicated. So for example, if you have a radio tower, essentially what happens is in order to create a wave, you have a circuit that creates an oscillation. So if, for example, I have a radio station that is creating that wave, you can see that this wave is propagating in time and space. Because if I picked a single point, like I picked this point that is closest, you can see that my electric field is getting larger and smaller. But I can also, if you look from left to right, you can see that that peak of that oscillation is propagating to the right. So you can see that the electric field is oscillating in the y direction, but that the wave is traveling in the positive x direction. Now with that, the magnetic field is not being shown, but I know that that magnetic field has to be perpendicular to both the propagation direction and the electric field direction, so that's going to be coming and oscillating in and out of the page for us. So you can see that if you change like the frequency of the oscillation, or the amplitude is going to be the height. So we're making that amplitude smaller. I can make the amplitude larger. Okay, that's going to be your value of E max or B max, is that amplitude. The frequency is going to be how often it oscillates. So I can change that frequency. Now notice that in order to get a higher frequency, you're having to get a larger amplitude wave. So they are actually linked together, and you can see that through our equation, because the ratio of E max to B max always has to equal the speed of light. Now this is a long video, so we're not going to watch this whole thing. But in this case, the purple is our electric field, and you can see that it's oscillating perpendicular to our magnetic field. If you follow the peak, say, of the electric field, it's moving kind of towards the right on the screen. That's our propagation direction. So you've probably heard of the electromagnetic spectrum. So the EM waves that we have been describing are the electromagnetic spectrum. So the equations that we have that relate the electric and magnetic field apply to every single type of electromagnetic radiation. So for this entire spectrum. So when you look at this diagram, there's a lot going on. So of course we have our wavelengths over here on the left. These are our long wavelengths. These are our short wavelengths. We have over here long wavelengths are going to have a low frequency because our speed of light is a constant. And it's equal to wavelength times frequency. So if my wavelength is long, I have to have a shorter frequency in order for that speed of light to be constant, or because the speed of light is constant. So we are going to have our low frequency waves over on the left and our very high frequency waves on the right. Frequency is also related to energy. And so energy is going to be H times F. That's going to be Planck's constant times the frequency. That's not part of this course, but you might have seen this in a chemistry course. And the idea is that your higher frequency waves are also going to have higher energy. So when you think about your high frequency, high energy waves, those are going to be your gamma and your X-ray. Those are the most dangerous types of rays. You know, gamma radiation, that's how we get the Hulk. X-rays, that is how we are going to be able to see through and take images of like our bones, because they pass through skin. On the other hand, our long wavelengths and our low frequencies are going to be over where radio is. Radio has a really long frequency, which is actually why radio waves are used for communication over very, very long distances. We have radio telescopes that are listening to stars and galaxies that are very, very far away. As you go towards the low to high microwaves, yes, those are the microwaves that we actually use to heat our food, are going to have a little higher energy than the radio waves. And then we start getting into the infrared, infra meaning below red, and our visible spectrum. And then ultraviolet is more dangerous than visible. Okay, that's why we wear sunscreen, especially the extreme UV over here on the right. That's what the ozone layer protects us from. The ozone layer absorbs the UV because the UV is used to break up the ozone, thereby absorbing that energy. If we did not have our ozone layer, the UV, that extreme UV is strong enough to be able to start causing cellular damage and could kill all life on Earth without the ozone layer to help protect us. So our visible wavelengths are kind of here in the middle, okay? They don't damage us very much at all, but a lot of high intensity light can hurt our eyes, and that's because when we look at the sun is actually emitting the full spectrum. The sun spectrum just happens to be weighted with most of the kind of peak. It's actually technically emitting green light. If the sun is kind of actually a yellow-green rather than just straight-up green. But it's actually emitting all of the wavelengths. Okay, we just have very, very little gamma and smaller amounts of kind of those very, very long radio waves. When you start looking at all of the different uses, you can kind of pause this and take a look, but we use the electromagnetic spectrum for most of our scientific purposes, okay? It's really, really awesome. The amazing things that we have figured out what we can do with all of these waves, not just light.